Welcome to The Explainer. Today, we are unpacking an absolutely incredible cosmic detective story. We're looking at the discovery of an ancient interstellar comet, literally a piece of another star system, that recently swept right through our neighborhood and completely upended our models of the universe. I'm so thrilled to walk you through the data and the stunning reality of an object that's been drifting through the void since way before our sun even existed.
Okay, let's dive into this. What exactly happens when a 12 billion year old relic crosses our solar system? I mean, this isn't just about a random rock passing by in the night. It's about an unprecedented opportunity. What can we actually learn from a pristine, ancient object that arrived from totally outside our cosmic neighborhood, carrying the chemical secrets of a completely different part of the galaxy? Well, the answer is a lot. And it forces us to question pretty much everything we thought we knew about how planets and comets form.
Section 1. An interstellar visitor arrives. Discovery and trajectory. So the story starts on July 1st, 2025, when the Atlas Observatory down in Chile caught an object moving on a wide-open, hyperbolic path straight out of deep space.
When it was discovered well outside the orbit of Jupiter, it was moving at an astounding 137,000 miles per hour. That sheer speed, combined with an extreme orbital eccentricity of 6.1, proved beyond a shadow of a doubt that this wasn't just some local comet getting flung around by Jupiter. No way. This thing was accelerated long before it ever encountered our sun. It's on the most aggressive, least bound path of any visitor we've ever tracked. Let's quickly break down its official designation, 3I/Atlas. The naming convention here is quite literal, but it's really important. The 3 tells you at a glance that humanity is still only 3 confirmed sightings into what is likely an entire population of these wandering objects. The I permanently distinguishes it as interstellar, meaning it was born outside our solar system. And Atlas, of course, honors the observatory that first spotted it. To really put 3I/Atlas into context, we have to look at our very short list of previous interstellar visitors. Back in 2017, we had 1I Oumuamua, which was cigar-shaped, tumbling, with absolutely no visible gas cloud or coma. Then in 2019, 2I Borisov arrived, and that behaved a lot more like an ordinary comet, with a dusty tail and familiar chemistry. But 3I Atlas? It doesn't neatly fit either of those templates. It has an active coma like Borisov, sure, but its extreme trajectory and totally unique chemistry put it in a class entirely by itself. Section 2. An unusual chemical fingerprint, the James Webb Space Telescope data. As 3I/Atlas moved closer to our sun, it started outgassing, and that gave our cosmic detective story its very first major clue. And this brilliantly illustrates just how bizarre this object is. In a typical solar system comet, water vapor totally dominates. But the James Webb Space Telescope found that the coma of 3I/Atlas is roughly 95% carbon dioxide. Water accounts for just a tiny 3% sliver, alongside 2% carbon monoxide. This is a genuinely layered, complicated mix of frozen materials, fundamentally different from what we see in our own cosmic backyard. So, what does that massive carbon dioxide spike actually mean? Basically, it formed in an unusually frigid environment far away from any star. A carbon dioxide-dominated coma strongly suggests the comet accreted its ice in an extremely cold region of a stellar disk, a place where carbon dioxide ice could form and survive much more easily than water ice. It is physical evidence of a completely different planetary formation environment.
Section 3. A 12 billion year journey, unlocking the carbon isotopes. We know it came from somewhere extremely cold, but when did it form? This is the second massive beat in our mystery. The contrast in age here is just staggering. Our entire solar system comes in at about 4.6 billion years old. 3I Atlas, however, clocks in at an estimated 10 to 12 billion years old. This object accreted its ice during cosmic noon, which was this intensely active period of star formation in the early universe. Think about that for a second. This comet has likely been drifting through the dark of interstellar space for longer than our sun has even existed.
So the crucial point is how scientists actually figured that age out. They used a chemical clock. As stars live and die over cosmic time, the ratio of carbon isotopes in the galaxy shifts. The James Webb data revealed that 3I's Atlas has extremely low amounts of carbon-13 compared to carbon-12. Furthermore, the water it did have was highly enriched with deuterium, which is heavy hydrogen. Together, these factors point squarely to an origin in the galactic thick disk, which is an older, more scattered population of stars. It paints a really clear picture of its ancient birth. Section 4. The missing iron mystery, the most puzzling anomaly. In October 2025, a brand new discovery pulled 3I/Atlas straight out of the specialists' journals and into global headlines.
The researchers were entirely baffled, explicitly calling the anomaly extremely puzzling. Why? Well, they detected a strong plume of nickel gas venting from the comet, but essentially zero iron. In nature, nickel and iron are forged together in supernovas. They travel through space bound together. They're practically cosmic twins. To see a strong nickel signal with the iron virtually absent from an icy body, tens of millions of kilometers from the sun, it completely defied standard comet chemistry. Naturally, an anomaly like this sparked an intense debate. On one side, we have the artificial hypothesis. Harvard physicist Avi Loeb pointed out that separating nickel from iron is primarily associated with industrial refining processes on Earth, suggesting a potential manufactured origin. Conversely, the overwhelming majority of the scientific community favors the natural hypothesis. They point to fragile, low-temperature molecules, like nickel carbonyls, that could naturally break apart and release nickel under weak sunlight while the iron remains locked away inside. It's a fascinating debate between a rare, undocumented natural comet chemistry and some pretty heavy fringe speculation.
But, as we know, good science tests every hypothesis. Because of the artificial speculation, researchers pointed the Allen telescope array directly at 3I/Atlas. The result? 0 artificial radio signals detected across a wide range of frequencies. This wasn't just a stunt. It was a rigorous, peer-reviewed technosignature search. It proved that when a wild question is raised, scientists don't just sit around and argue. They use real instruments to check. And in this case, they found absolutely no evidence of a transmitter.
Section 5. Redefining planet formation. A rare external check. Beyond all the dramatic headlines, why does this specific interstellar object matter so deeply to the future of planetary science?
Let's move to and see how this builds across its transit timeline. 3I/Atlas safely sped through our solar system, offering unprecedented vantage points. In October 2025, it passed close to Mars and hit its closest point to the Sun. By November, it passed Venus. Its closest approach to Earth was in December 2025, at a very comfortable, very safe distance of 270 million kilometers, posing absolutely zero threat, before swinging past Jupiter in March 2026. At every single stop on this timeline, orbiters and telescopes were capturing a massive wealth of data. And thanks to the Hubble Space Telescope separating the solid nucleus from the glowing coma, we got a highly refined measurement. The object is a massive 2.6 kilometers in diameter. This confirmed that 3I/Atlas was a genuinely large chunk of ancient history. It's notably bigger than Borisov, and that size allowed for the kind of direct close-up scrutiny from spacecraft that prior interstellar objects simply never received. The legacy of 3I/Atlas is profound. It represents our very first direct chemical sample from a completely different star system. For the first time, scientists aren't just looking at local comets. They are actively testing if planet building is a universal recipe, or if it drastically changes based on the local environment. It forces us to rethink how metals like nickel and iron behave in extreme cosmic cold. And long after it's gone, it leaves behind an unprecedented, massive data set for researchers to study for decades to come. 3I/Atlas is now receding back into the dark of deep space, moving at over 60 kilometers a second, never to return. But that leaves us with a huge lingering question. What will the Vera Rubin Observatory find when the next interstellar visitor arrives? You see, the newly operational Rubin Observatory in Chile is explicitly designed to catch these fast-moving visitors early. 3I/Atlas proved these ancient relics are out there, regularly crossing our path. So it's really not a matter of if we find the fourth one, but when, and what 12-billion-year-old secrets it will carry with it. Thank you so much for joining me on this incredible journey through the data. Keep looking up, and as always, stay curious.